Hello again. So here in this demonstration, we will show how to simulate the behavior of an active antenna for beam steering application in real life use case with the simulation. So here it's an antenna which has been designed for aerospace defense applications by XLIM, a laboratory based in Limoges in France. And here we have different different antennas on the same system in order to steer the angle of the emitted signal in different directions. When you perform such an application, in fact, the beam steering angle will create some perturbation because of the coupling effect between all these different antennas on the RF front end, which feeds the signal to the different antenna. And this is the phenomena that we would like to simulate in order to understand what's going on into the real system when this one is operating. So here in this simulation template, we have our system which has been designed. Here we have 36 different power amplifiers which works in parallel in order to feed the antenna. On the output, here we have the antenna model, which take into account all the coupling effect between all these antennas. So in fact, we have done an electromagnetic simulation which provide all the S parameters which describe the antenna behavior. Because we are able to plug this antenna model to the HPA model, we are able to take into account all the phenomena, the load pull effect, active load pull effect that takes place at the power amplifier level depending on the beam steering. And this is what we would like to simulate today. So in front of our system, we have the RF source here. The RF source which feed the signal to the 36 power amplifier. So let's run the simulation. So here we simulate a beam steering angle that will shift from minus 80 degree up to plus 80 degree with a 1 degree step. So the simulation is very fast, and once this one has been done, we can display the result here into the whiteboard module in order to show this phenomena. So here we have an element of the antenna, and we can shift the different antenna in order to observe the behavior of the power amplifier for each module. So in this example, this port has a load impedance which will be provided to the HPA. And we can see that difference between, depending on the beam steering angle, in fact, we will create some load pull effect on all these power amplifier. And obviously, because the load impedance change, it will modify the power amplifier performance. So here you can see the variation of the output power on the PA as a function of the beam steering angle because of this modulation effect on the load impedance seen by the PA. And we can observe this phenomena for all the different ports of the antenna. And this is very important to take into account because if it's not well managed, then you will degrade the power amplifier performance, and you will think that you will send the signal into a certain direction, but in fact, it will not be the exact direction. This is why it's very important to take into account this load pull effect on the PA as a function of the beam steering. Why we are able to perform such a good simulation? It's because, in fact, we have been able to extract behavior model of power amplifier that take into account the load pull effect. So for that, we use a load pull setup in order to extract the data on the measurement bench, such as a load pull system provided by Maury Microwave, for instance. So it was the first system simulation scenario. We have a second one, which is about power amplifier simulation just for one amplifier in order to better understand what's going on. So in that case, we will use another schematic. So here we have our power amplifier, and we would like to understand what will be the performance of this amplifier when this one will be linearized. So in order to anticipate these performances in linearized conditions, we put in front of the amplifier a DPD model. So this one has been defined by the user. In that case, it's a GMP DPD model, which is applied on the power amplifier. And we have a second block in here, which is a Matlab block, which calculates the coefficient of the DPD performances. At the input, we have our modulated signal that will send a signal such as a 5G signal, for example, with a 100 megahertz bandwidth. Once we have done this simulation, we can observe the performance in the whiteboard in order to see what the impact of the DPD on the power amplifier performance. So here, in that case, we have done different iterations in order to optimize the performance. So we have our output spectrum here and the dynamic IM performances of the power amplifier. So let's try to move the iteration. We can see that as if the higher the number of iterations, the higher the linearity. So this is very convenient in order to estimate very shortly what will be the performance. So we have the same for the IM characteristic in order to see what the result of the DPD operating conditions. The main point of this demo, what's the problem solved, in fact, when you are using alternative solution, such a simulation really takes a very long time. It could be a day or two of simulation if you want to use a very wide band signal and with a simulation in time domain mode. Because vision models are very accurate and very fast for simulation, you can anticipate the performance of your linearized amplifier in a timely manner. And this is where we have the most added value, because in fact it really accelerates the design flow at the system level for the system architect. And because of that, you can simulate, for example, in a circuit simulator such as ADS from Keysight, you can simulate, for example, different biasing circuit of your power amplifier. You generate the data, and then you take this data, you forward them to vision, you will extract your behavior model, and you will simulate in real time what will be the optimized performance with digital signals. I hope you enjoyed this presentation, and we are there to answer further questions. Thank you very much.